Welcome to this Concept Explainer, brought to you by CBSE ScoreLab of ProfSam.com. That is ProfSam.com. Today we're taking a deep dive into a really crucial device from Unit 4, Moving Charges and Magnetism. We're talking about the Moving Coil Galvanometer. Our mission is simple, to make this concept so clear that you can explain it to anyone and, of course, score full marks in your exams. Okay, so let's start with a very basic question. We all know that electricity flows in a circuit, but how do we actually know if the current is, say, 1.5 amperes?
Right.
Or the voltage is 1.2 volts? I mean, what instrument is actually converting that invisible flow into a visible number on a dial?
That would be the galvanometer, right? We see it in every lab experiment, but it always looks so delicate. It feels like you could break it just by looking at it the wrong way.
That delicate look is the whole point, and this is where it gets surprising. We are focusing on that exact device,
Yeah.
the Moving Coil Galvanometer, or MCG. And it's not just delicate, it is incredibly sensitive. I mean, it can show a full-scale deflection for currents in the microamperes. Tiny, tiny currents.
Wait, microamperes? That's practically nothing. So if it's so good at detecting small currents, why are we always warned not to use it directly in a circuit? It seems a bit contradictory, isn't it?
That is the central paradox of the MCG. Sensitivity is also its weakness in a way. You see, the coil has a relatively large resistance, maybe 60 ohms or so.
Mm-hmm.
Now, if you put that 60 ohm device in series into a circuit that only has, say, 3 ohms of resistance, you completely change the circuit. The measurement becomes useless, so we have to modify it. So let's break down the core idea first. At the most basic level, the MCG is a device that it uses the magnetic force from a current to measure that current. The whole idea is we convert electrical current into mechanical rotation, and then we simply measure how much it has rotated.
Okay, so we're turning an invisible electric flow into a visible mechanical twist.
Exactly. And to understand this, let's use a very simple analogy. Think of a spring weighing scale, the ones they use for vegetables. The current flowing through the coil. That's like the weight you put on the scale. This weight creates a downward turning force. In our device, that's the magnetic torque.
And the spring in the scale pushes back up.
Precisely. The spring provides an upward restoring force, a counter torque. And the pointer stops only when those two forces, the magnetic pull and the spring's pushback, are perfectly balanced. The entire device is built on this idea of equilibrium.
That makes sense. But how does it stop so neatly? With such a delicate coil, I'd imagine it would just keep oscillating back and forth.
That's a very sharp question. It's about the engineering. The spring provides a restoring force that's proportional to the twist. So the more it twists, the harder the spring pushes back. There's also something called electromagnetic damping, but the spring is the main hero here. So let's build a mental image. Just picture a rectangular coil of wire hanging by a thread, basically, between the poles of a strong magnet.
Okay, I can see that.
When current flows, the coil gets a kick. It wants to twist, like you're twisting a doorknob. But attached to it is this very fine spring that resists that twist. The pointer stops when the magnetic twist is exactly perfectly canceled out by the spring's resistance.
And this whole principle, putting a current loop in a magnetic field to get torque, this is the practical application of what we studied earlier, the tau math BFM times math BFE formula, correct?
Absolutely. This is where theory becomes a tool. It takes that abstract formula and builds a real precise instrument. It really unifies the whole unit. Now, you mentioned the magnetic field. This part is genius. The field isn't uniform. It's designed to be radial. Why do you think that is?
In a normal field, the torque depends on the angle, right? Because of the sine theta term.
Yeah.
So as the coil rotates, the torque would change.
Exactly. And if the torque keeps changing with the angle, your scale would be completely nonlinear. 1 ampere might move the needle a little. The next ampere might move it a lot. It would be useless for measurement.
Ah, okay. So the radial field is there to solve that problem.
It solves it brilliantly. By using curved pole pieces and a soft iron core inside, the field lines are always pointing along the radius. This clever setup ensures that the magnetic field is always parallel to the plane of the coil, which means the angle theta is always 90 degrees and sine theta is always 1, maximum torque all the time. And because the torque is constant and maximal, the deflection of the pointer is directly, beautifully proportional to the current. That gives us our nice linear scale. Okay, now that we have the physical picture, let us look at how insert formally defines this. Could you please read the exact definition about the balance of torques?
Of course. It says, the magnetic torque NIABB line tends to rotate the coil. A spring's phi provides a counter-torque balance that balances the magnetic torque NIABB, resulting in a steady angular deflection pile. In equilibrium, NAB exceeds NIABB, where $, is the torsional constant of the spring. i.e. the restoring torque per unit twist.
Perfect. That one equation, K phi equals NIAD bale, is the heart of the galvanometer. Let's just quickly walk through it step by step. Step 1 is the engine. The current I flowing through N turns the coil. Step 2 is the setting. The coil sits in that strong radial magnetic field, B. The soft iron core makes B stronger and radial. Step 3, the force. This creates the magnetic torque, tau equals NIAB. Remember, sine theta is 1, so it's the maximum possible torque. Step 4 is the resistance, the spring. It provides a restoring torque. Tau equals tau. Here, tau is just how stiff the spring is. And finally, step 5, the balance. At equilibrium, the magnetic torque equals the spring torque. NIAB equals K phi. If you just rearrange that a little, you get tau NABK times AEB. Since N, A, B, and K are all constants for a given device, deflection is directly proportional to the current, I. Simple. Hope everything is clear so far. This concept explainer is from ProfSam.com. That is PROFSAM.com. Now let's get back to that practical problem. We know the MCG works, but we can't use it directly because of its high resistance to large shitters. Let's take a quick example.
Imagine a circuit with a 3-volt source and a 3-ohm resistance.
Okay, so the current there should be V volars, which is 3 divided by 3.1 ampere. That's the true current.
Correct. Now let's try to measure that current by putting our galvanometer, which has a 60-ohm resistance, in series. The total resistance of the circuit suddenly becomes 3 plus 60, 63 ohms.
Oh, I see. And the new current is 3 volts divided by 63 ohms, which is almost nothing. It's less than a 0.05 amperes. The device has completely changed the thing it was supposed to measure.
Exactly. The act of measuring destroyed the measurement. So we must convert the galvanometer. First, let's make an ammeter. An ammeter is connected in series, so it must have a very, very low resistance, almost zero. How do we make a 60-ohm device have almost zero resistance?
We use parallel connections. If you add a resistor in parallel, the total resistance becomes smaller than the smallest one.
You got it. We connect a tiny, tiny resistance, we call it a shunt in parallel with the galvanometer coil. Most of the current then bypasses the delicate coil and goes through this shunt. The overall resistance of the ammeter becomes very low, and it doesn't disturb the circuit anymore.
Okay, so for an ammeter, we use a small shunt in parallel. What about a voltmeter?
Good question. A voltmeter is connected in parallel across a component. So, to avoid changing the circuit, it must draw as little current as possible.
Which means it needs to have a very high resistance, the opposite of an ammeter.
The complete opposite. To convert the MCG into a voltmeter, we connect a very large resistance, maybe thousands of ohms, in series with the coil. This makes the total resistance of the voltmeter extremely high, so when you connect it in parallel, it barely draws any current, and the voltage you're measuring remains accurate. Okay, now let us talk about the silent killers. These are the common misconceptions that can cause you to lose marks in the exam. Misconception number 1. The wrong idea is that the magnetic force does work to accelerate the coil. It seems logical, no. Force causes motion, so it must be doing work.
But wait, the magnetic force on a charge is always perpendicular to its velocity, and work is force times distance in the same direction, so
So the work done is zero. That's the correct idea. The magnetic force on any single charge does no work. However, and this is the key, the net torque on the entire loop does do work against the spring.
Okay. So force on a charge, no work. Torque on the loop does work.
That's the distinction. Just remember this. Magnetic force curves, magnetic torque twists. Okay, second misconception. The wrong idea is that high current sensitivity automatically means high voltage sensitivity.
But don't they both depend on the number of turns, N? So if you increase N, both should increase.
That's the trap. You are right. Current sensitivity, SI, is proportional to N. So you double the turns, you double the sensitivity, great. But to double the turns, you've doubled the length of the wire, which means the coil's resistance, RG, also doubles. And voltage sensitivity, SV, is proportional to N divided by RG.
Oh, so the doubling on the top and the doubling on the bottom just cancel out. The voltage sensitivity doesn't change at all.
Not one bit. You see the trap? So remember, sensitivity is not a simple more is better. Current and voltage sensitivity are independent. The last one, the wrong idea is that the soft iron core is only there to make the magnetic field stronger. That's only half the story.
The other half must be about the radial field we discussed earlier.
Exactly. That is the correct idea. The core does two things. One, it strengthens the field because it's ferromagnetic. Two, its cylindrical shape is what makes the field lines radial. And that radial field is what gives us the linear scale. Without it, the device is useless. So always mention both points. Just remember, the soft iron core is strong and smart. All right, now let's lock this in with some memory anchors. For the main equation, AU, D, A, R, E, I, way, of C, I, S, E, D, K, It links all the parts together. Number of turns, area B field, spring constant K, and current I, DOB KI.
Okay, that's easy to remember.
Good. Now for a physical gesture. Hold your right hand flat, that's the coil. Curl your fingers in the direction of the current. Your thumb now points up. That's the direction of the torque, the twist. Now, use your other hand to gently resist that twist. That's the spring, the K. Feel that balance, the magnetic twist against the spring's resistance.
The twist and the resistance. Got it. It makes the balance equation feel more physical.
And a simple phrase to tie it all together. Perpendicular push balanced by spring twist. Okay, let's wrap this up. Here's the 3-point summary for your exam. Point 1. The moving coil galvanometer uses the magnetic torque, tau, NIABB, on a current-carrying coil in a radial magnetic field to produce a measurable rotation. Point 2. A stable deflection is achieved when this magnetic torque is balanced by the restoring torque from a spring. This proves that deflection is directly proportional to the current if you prop to LA. And point 3. An MCG must be converted. You add a small shunt resistance in parallel to make a low-resistance ammeter or a large resistance in series to make a high-resistance voltmeter. To get maximum marks in 12th CBSE Physics, Chemistry, and Maths, visit ProfSam.com.
That is ProfSam, right?
Yes, ProfSam.com. Thank you for joining this deep dive.
Thank you. This was very helpful.